In note 6.2, example 3, we are going to use special right triangles. So that's 45, 45, 90-degree triangles and 30, 60, 90-degree triangles. So to derive trig ratios for commonly used angles. So we're going to think back to geometry, and we are going to set up the angles and the side lengths in these special right triangles. So we're going to start with a 45, 45, 90 right triangle. So we're given one acute angle here, 45, and we're given the right angle. By the triangle angle sum theorem, we know that the missing angle here is 45 degrees, right? Because we need an angle that's complementary to 45 degrees. So that angle is 45. And now I have labeled one of the legs as having a side length of A. And now to find the other ones, we know that this is an isosceles triangle. So in isosceles triangle, the side lengths are, the legs are equal. So this other side length is A. And then we can find the length of the hypotenuse. We can use the Pythagorean theorem. So we can have that A squared plus A squared is equal to, let's call this C for now, is equal to C squared. So we'll have 2A squared is equal to C squared. And now we'll take the square root of both sides. So C is equal to rad 2. And we normally put the A on the outside. So A rad 2. So when the legs have the length of A, the hypotenuse has a length of, I'm going to just write this as A rad 2. And hopefully you remember that from geometry. So this is the hypotenuse. I'm labeling it relative to the 45-degree angle. This would be the opposite, and this will be the adjacent side. Now we're going to go over and look at a 30, 60, 90-degree right triangle. So here we've labeled the 60-degree angle. So that means that the missing acute angle is the complement of 60 degrees. So that will be 30 degrees. And now we know that we're given the side opposite the 30-degree angle, which we're told is A. And if you don't remember the derivation, I will derive this quickly for you. So the way it works is we take an equilateral triangle and we draw in an altitude. When we draw on that altitude, that cuts this top angle in half. So each one of these angles up here is 30 degrees. And if we say that this is an equilateral triangle where all sides have a length of 2a, so if it's 2a at the bottom, when we draw on the altitude, we cut the base in half. So each one of these halves here has a length of A. So this has a length of A, the hypotenuse has a length of 2A, and then we are going to try to find, or we are going to find the length of the altitude. So we want to find this length. I'll call it X for the purpose of our derivation. And now we can use the Pythagorean theorem with one of these triangles, one of these 30, 60, 90-degree triangles. So we would have that A squared plus X squared is equal to the length of the hypotenuse squared, which is 2A squared. And then we want to solve for A. So we are going to have, we want to solve for X. So X squared is equal to 4A squared minus A squared. So X squared is equal to 3A squared. Take the square root of both sides. And so X is equal to A rad 3. So I'm going to put that onto our triangle. So this is A rad 3. So I'm going to put those lengths onto the little right triangle that you have on your paper. So if the side opposite the 30 has a length of A, then the hypotenuse up here has a length of 2A, and the side opposite the 60-degree angle, which was the altitude in our derivation, has a length of A rad 3. So this is the opposite. This is the adjacent relative to the 60-degree angle. All right, so now we're going to use these special right triangles to find the six trig ratios for 30-degree, 45-degree, and 60-degree angles, or in radians, pi over 6, pi over 4, or pi over 3. So in each case, we're going to look at the special right triangle. So we're going to start with the 30-degree angle. So I'm going to label the side lengths relative to the 30-degree angle here. So I'm going to go, the hypotenuse is still the hypotenuse. The side opposite the 30 is this one here. So relative to the 30-degree, this is the opposite. And then the third side here is going to be the adjacent. All right, so we're going to be looking at these black labels on that 30, 60, 90 triangle. All right, so we want to know sine of theta. That's when theta is 30. That's going to be the length of the opposite side. So A over the length of the hypotenuse, which is 2A. So I'm going to have A over 2A. I'm going to simplify this. It's going to give me 1/2. Then we're going to do the cosine of 30. So that's going to be the length of the adjacent side, adjacent to the 30. So A rad 3 over the hypotenuse, which is 2A. So this is A rad 3 over 2A. The A's canceled out, leaving us with rad 3 over 2. Tangent theta relative to the 30-degree angle is the length of the opposite side over the length of the adjacent side. So that is going to be A over A rad 3. And then that becomes 1 over rad 3. And then we'll rationalize it, which becomes rad 3 over 3. Next, we're going to do cosecant theta. So cosecant theta is the length of the hypotenuse over the opposite side, or we can just take the reciprocal of this value from sine that we found. So if we do the length of the hypotenuse, that's 2A. The length of the opposite side relative to the 30-degree angle is A. So cosecant 30 is 2. Secant theta is the length of the hypotenuse, which is 2A, over the adjacent side, which is A rad 3, or you can take the reciprocal of cosine. This becomes 2 over rad 3, then rationalize, and you get 2 rad 3 over 3. And then cotangent theta is the length of the adjacent side, which relative to the 30-degree angle is A rad 3 over the length of the opposite side, which is A. So this simplifies to rad 3. We're going to do the same exercise now for the 45-degree angle. This we're going to focus on the 45, 45, 90 right triangle. I've already labeled the side lengths adjacent, opposite, and hypotenuse relative to the 45-degree angle in the lower right of the triangle. So let's go ahead and define these or find these values. So sine of theta is the length of the opposite side. So the opposite side is A over the hypotenuse is A rad 2. So we have A over A rad 2. Cancel out the A's. You get 1 over rad 2 and then rationalize. So you get rad 2 over 2. Cosine theta is the length of the adjacent side over the hypotenuse. It's actually the same thing we just found. So it's A over A rad 2. The A's cancel out. Rationalize the denominator. We get rad 2 over 2. Tangent theta is the length of the opposite side, A, over the length of the adjacent side. So it's A over A, which simplifies to 1. Cosecant theta is the length of the hypotenuse. So A rad 2 over the opposite side, which is A. So this is A rad 2 over A, which simplifies to rad 2. Or we could simply take the reciprocal of sine. Let's see, we're at secant theta. We could take the reciprocal of cosine, or we can go to the definition, which is the length of the hypotenuse, A rad 2, over the length of the adjacent side, which is A. So this simplifies to rad 2. And then the last one, cotangent theta, is the length of the adjacent side. So the adjacent side is length A over the opposite side, which is length A. So we have a over a, which is equal to 1, or you could also take the reciprocal of tangent theta. So the reciprocal of 1 is 1. All right, we're going to do the last set here. So we are going to look at the 30, 60, 90 triangle, and we're going to focus on the 60-degree angle. And I have marked the side lengths in red for the 60-degree angle. So we have adjacent, opposite is a rad 3, hypotenuse is still 2a. So let's go ahead and set up these 6 ratios. So sine of 60 is the length of the opposite side. Here, the opposite side is a rad 3 over the hypotenuse, which is 2a. So this is a rad 3 over 2a. The a's cancel, leaving us with rad 3 over 2. Cosine theta is the length of the adjacent side, which is in red here, a over the length of the hypotenuse, which is 2a. So this is a over 2a, which is 1/2. Tangent theta is the length of the opposite side. I just erased this by mistake. So the length of the opposite side, which is a, over the length of the adjacent side, which is, the opposite is a rad 3 over the adjacent side, which is a. So this is a rad 3 over a. The a's cancel out, we get rad 3. And then we will do the reciprocal functions. So cosecant theta, we could take the reciprocal of sine, or we can do the length of the hypotenuse, which is 2a, over the length of the opposite side, which is a rad 3. So this is 2 over rad 3 after canceling out the a's. We rationalize the denominator. We got 2 rad 3 over 3. And let's scroll this up a bit. Secant theta, that's the reciprocal of cosine, or we can use the side lengths. So our side lengths here are going to be the length of the hypotenuse, which is 2a, over the length of the adjacent side, which is a. So secant theta is 2, which makes sense, as that's the reciprocal of cosine, which was 1/2. Cotangent is going to be the reciprocal of tangent, or we can use the definition. So we want the length of the adjacent side, which is a, over the length of the opposite side, which is a rad 3. The a's cancel out, leaving us with 1 rad 3. Rationalize the denominator, and we get rad 3 over 3. And if you look at this chart, you will notice a lot of patterns. And in particular, I want to point out that the sine of 30 is the same thing as the cosine of 60. We also have that the cosine of 30 is the same as the sine of 60. And if you think about 30 and 60, these are complementary angles. So it looks like the sine of the sine of 30 is equal to the cosine of the complement of 30. And we're going to talk about more on the next page. You will need to know these trig ratios of all these special angles. And you should either learn how to construct them using the special right triangles, or you'll end up possibly memorizing these values, because we are going to be using them very often.